Uh, we would be learning how to analyze a ultra low temperature refrigeration system, or what is also known as the Cascade refrigeration system. In the Cascade refrigeration system, which is generally used for achieving a lower temperature, lower like minus 70 degrees centigrade, minus 80 degrees centigrade in some biomedical applications, uh, there you basically use two loops. One is the low temperature loop of refrigeration cycle, and other is the high temperature loop of the refrigeration cycle. So the high temperature loop is called as a high temperature cascade, and the low temperature loop is called as a low temperature cascade. In each cascade you would have two heat exchangers. This is one heat exchanger, this is the other heat exchanger, and then there are two devices to change the pressure, that is, this is a compressor and this is the expansion device. Similarly, the loop upper loop, that is a high temperature cascade, also has a heat exchanger which is common to the low temperature heat exchanger, and there is a compressor, there is a condenser, and there is expansion device. So you see that one heat exchanger is common, and this heat exchanger which is common is known as the cascade heat exchanger. uh, Let us say that you want to achieve minus 70 degrees centigrade, and the surrounding temperature is such that the condensation has to happen at 50 degrees centigrade. So let us solve one numerical wherein I would take some typical values of low temperature refrigeration system, wherein the evaporator temperature is, let us say, minus 70 degrees centigrade, and the condensation has to happen in the condenser at 50 degrees centigrade. Now, if you use a single refrigerant and a single loop, the problem is that it will have to operate at a very high pressure ratio. Pressure ratio means the condenser pressure to the evaporator pressure. This ratio becomes extremely high and unmanageable if we use a single loop. Instead, if we use two loops, wherein, as shown here, a lower temperature loop shown in black and a higher temperature loop shown in red, with two refrigerants, the high temperature loop with propane as a refrigerant and the low temperature loop with ethane as a refrigerant. In that case, the pressure ratio becomes manageable. Now, in the low temperature loop, as you see over here, I have used ethane as a refrigerant, which is R170, and in the high temperature loop, I see that there is a propane as a refrigerant, which is R290. What happens is, we'll try to understand what happens is following. In the low temperature loop, similar to your regular refrigeration cycle, you would have the low temperature refrigerant evaporating in the evaporator, then it would be compressed in the compressor, then it would go to the common heat exchanger, which is known as the cascade heat exchanger, and then it would expand. So this is similar to your single stage vapor compression refrigeration cycle. The only point is you have two refrigerants. So here the refrigerant is now, as you see, ethane, and here the temperature is minus 70, right? And if you look at this diagram carefully, you would find that this refrigerant would condense at minus 35. So it means that the cascade condensation temperature, is happening at minus 35 degree centigrade. Okay, so for this lower loop, low temperature cascade, the pressure ratio would be Psat corresponding to minus 35 upon Psat corresponding to minus 70 degrees centigrade. This would be the pressure ratio of the low temperature cascade. And in the high temperature cascade, again what you have is, here you have a cascade heat exchanger, here you have the condenser, then the compressor in the high temperature loop, and an expansion valve. And here instead of ethane you have propane which is being circulating, right? So it means now, as already told, the condensation temperature is 50 degrees centigrade, and this cascade heat exchanger evaporation would happen at a lower temperature than the cascade condensation temperature. So lower than minus 35. So let us say that it is lower than minus 35. It is minus 40 degrees centigrade is the cascade evaporation temperature. Okay, so minus 40 degrees centigrade is your temperature of the cascade heat exchanger, cascade evaporator. Okay, so cascade evaporation for a high temperature cascade happens at minus 40, and condensation happens at 50 degrees centigrade. So the pressure ratio of this would be P sat, saturation pressure corresponding to 50, upon saturation pressure corresponding to minus 40. So this pressure ratio and this pressure ratio, they become manageable as compared to a single loop pressure ratio. So this is the advantage of cascading. Now if you want to solve this numerical, what I need to do is that I need to get this enthalpy. So this is 1, this is 2, this is 3, this is 4. So the enthalpy at 1, enthalpy at 2, enthalpy at 3 is equal to enthalpy at 4. This I'll have to find using the pressure enthalpy chart of ethane. So if you refer to the pressure enthalpy chart of ethane and corresponding to our temperatures, what you'll find is that for ethane you would have some values, and say around 500 or something like that, and you'll get some values of at H2, H1, H3 and H4. So I'm not sure, but if you refer to the pH chart, probably you would get the value of H3 and H4 as 135, round about that, kilojoule per kg, and probably this H1 would be around 535 and H2 would be around 460. You can just refer to the pH chart of ethane and convince yourself, okay, that these are the values. Okay, so once you get these values, okay, you can then easily find out what is the compressor work of this compressor, which has to be H2 minus H1. Similarly, you can find the refrigerating effect, okay, which is H1 minus H4, which is the specific refrigerating effect. Okay, so if let us say that you are given the capacity of this, say let us say that the capacity given for a low temperature cascade or is 300 watts. So if this is 300 watts, then it means m dot into H1 minus H4 would be 300 watts. So that helps us to calculate the mass flow rate of the refrigerant passing through the low temperature cascade. Okay. So if you refer to this, so how do you find the mass flow rate? The mass flow rate can be found out as the enthalpy difference. So this is 1, this is 2, this is 3, this is 4. So how do you find the mass flow rate? Knowing the capacity QL upon H1 minus H4. In my problem, so suppose this is 300 watts, and then I have the values of H1 and H4. From the pH table, I get the value of m dot. Okay. So this is how you get to calculate the mass flow rate of the low temperature cascade. The value which I had obtained is around, it is approximately 0.8 kg per second. Okay, 0.8 into 10 raised to minus 3 kg per second. This you can look at the actual values from the pH chart. So suppose this is 535. This is 535 minus 135 up, and just divide 300 by, upon H1 minus H4. You will get the mass flow rate, which is the refrigerant mass flow rate flowing through the low temperature cascade. Okay. Now what would happen? What would happen is this heat has to be rejected in the low temperature cascade, and where it will go? It will go here. Okay, so the heat which is rejected by this cascade heat exchanger would go again into the cascade heat exchanger upper temperature loop, high temperature loop. That is, it will be taken by propane, which should evaporate at minus 40 degrees centigrade. So the energy exchange would be like this. The condenser, cascade condenser, which is having ethane, would reject the heat, and the cascade evaporator, which is having propane, would absorb the heat. Okay, so the energy balance becomes like this. The heat rejected by the cascade condenser, this means H2 minus H3. Okay, H2 minus H3. So this is m dot H2 minus H3, and this m dot is of ethane. What is this? This is the heat which is rejected by the cascade heat exchanger. What we are doing is we are writing an energy balance where the heat rejected by the cascade condenser, that is ethane, is equal to the heat gained by the cascade evaporator, which is nothing but having the refrigerant propane, right? So if that is the case, then m dot H2 minus H3 would be equal to m dot of propane now into delta H across the evaporator. So what is this? So if you look at the diagram carefully, you will find that what is happening here is this is 5, this is 6, this is 7, this is 8. The heat which is rejected, okay, by the ethane is going to come to propane, okay, and that would be increasing its enthalpy. So m dot of propane into H5 minus H8 would be the heat gained by propane. Okay, so the energy balance is like this: H5 minus H8. So m dot ethane into H2 minus H3 is equal to m dot propane into H5 minus H8. This is the energy balance for the cascade heat exchanger, that is cascade condenser and cascade evaporator. So if you are clear on this, then you can easily find the mass flow rate of propane. So let me do this. For that, before that, I need to find this values of H5, S6, S7, H8. How do I do that? I refer to the pH chart of propane. And I find the corresponding values of 5, 6, 7, 8 from the pH diagram. So that values, they come around. H5 in my case comes around 525 kilojoule per kg. H6 from the pH chart comes to around 650 kilojoule per kg, and H7, which also happens to be H8, comes out to be around 320. Now how do I get that? This is simple. Okay, you just draw this pH chart and get these values as 5, 6, 7 and 8. Okay, so once you get this and then you use the energy balance, what you will obtain is the following: M1 or M of ethane into H2 minus H3 is equal to m of propane into H5 minus H8. So if you put these values, the values of corresponding enthalpies and the values of mass flow rate of ethane, you will get the mass flow rate of propane, okay, and that comes to around 1.8 into 10 raised to minus 3 kg per second. Okay, you might get a different value depending upon how accurately you are extracting the enthalpy values. So once you get the mass flow rate of propane and mass flow rate of ethane, you can find out the power consumed by the compressor of low temperature cascade, that is handling ethane, and that would be equal to mass of ethane into H2 minus H3. Look at this, okay. This is the pH diagram for low temperature cascade. 1, 2, 3, 4. Okay, so H2 minus H1. This is your compression. And similarly, power consumed by the compressor of high temperature cascade, that is handling propane, would be mass flow rate of propane into the corresponding enthalpy difference across the, that is 5, 6, 7 and 8. It means H6 minus H5. If you put these values from the pH chart, you will get this value to be around 230 watts. Okay, this is 230 watts and this would be around, in my problem, it is around 72 watts. Okay, so then if you want to find the COP, coefficient of performance, then coefficient of performance would be what? If you look at this diagram carefully again, coefficient of performance would be what? It would be the refrigerating effect, that is QL, upon the power consumed by this compressor and this compressor. So QL upon PC1 plus PC2 would be the refrigerating effect. In this case, I will just show this 5, 6, 7 and 8 over here. Okay. On this 5, 6, 7, 8. Okay. So the coefficient of performance then would be, COP would be the refrigerating effect, which is 300 watts upon the power consumed by the compressor 1, which we have found to be 72 watts, and the power consumed by the compressor 2, which we have found to be 232 watts. So it means that this is around 70 plus 230 approximately. Okay, so this is approximately 1. So this is how we analyze the ultra low temperature refrigeration system. And what is important is two things. One is that you are referring to two pressure enthalpy diagrams for getting the properties, that is getting the enthalpies. And the second thing you need to understand is we are doing an energy balance for this cascade heat exchanger, where the energy which is rejected by this condenser, okay, is absorbed by the energy which is of the high temperature loop. That is, energy rejected by the condenser handling ethane is absorbed by energy which is taken in the evaporator by propane. So this energy balance you have to understand. Otherwise, the analysis is simple. Okay. Hope you understood the analysis of ultra low temperature refrigeration system, namely the cascade refrigeration.